Okay, welcome to the third and final part of this series where we'll be discussing the exponential form. We'll discuss De Moivre's theorem and solve equations and roots of complex numbers. Some of you will be familiar with Taylor series or Taylor expansions, where we can write cosine of x as 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus etc. etc. Sine of x can be written as x minus x to the power of 3 divided by 3 factorial plus x to the power of 5 divided by 5 factorial, and this series continues. And e to the power of x can be written as 1 plus x squared over 2 factorial plus x to the power of 3 over 3 factorial plus x to the power of 4 over 4 factorial, etc., etc. Now let's take x to be equal to theta times j, and let's plug this into e to the power of x. E to the power of theta times j is equal to 1 plus theta times j plus theta squared times j squared over 2 factorial plus theta squared times, theta to the power of 3 times j to the power of 3 over 3 factorial plus theta to the power of 4, j to the power of 4 divided by 4 factorial, etc. Now, we know that if x is equal to theta times j, x squared is theta squared times j squared, which is minus theta squared. X to the power of 3 is equal to minus theta to the power of 3 times j. X to the power of 4 is equal to minus theta to the power of 4 times j squared, so we get theta squared again. And this list continues. And what we see, well, we can rewrite this. This is 1 plus theta times j minus theta squared divided by 2 factorial minus theta to the power of 3j divided by 3 factorial plus theta to the power of 4 divided by 4 factorial, and this continues. And we can see this series and we can split it into two parts. We have the blue parts and we have the red parts. And if we take this series and we take the blue parts are equal to cosine of theta. And the red parts are equal to j times sine of theta. So we can write e to the power of I theta as cosine theta plus j times the sine of theta. And so we'll derive a couple of identities here, but this shows you that there's another form of a complex number, z equal to r cosine theta plus j times the sine of theta, can now be written as r e to the power of, this has to be a j times theta. And this is, I think, the fourth form of a complex number. We also see that we can write the complex conjugate of z as r e to the power of minus j times theta. So let's return to this identity here. If we look at e to the power of j theta equal to cosine of theta plus j times sine of theta, and we have e to the power of minus j theta is equal to cosine of theta, because cosine of minus theta is the same as cosine of theta. The sine of minus theta is minus the sine of theta, so this is minus j sine of theta. If we were to add these two together, these two sine terms would cancel out. We would be left with 2 times cosine, but we get that cosine of theta is e to the power j theta plus e to the power of minus j theta divided by 2. This is one identity, and if we want the sine of theta, we have e to the power of j theta minus e to the power of minus j theta divided by 2j. And these are just different ways of writing our familiar cosine and sine functions in terms of the exponential form of a complex number. And we use that cosine of minus theta is the cosine of theta, and the sine of minus theta is minus the sine of theta, two identities from geometry. Now, if we use this exponential form, z is e to the power of j theta, and that is equal to cosine of theta plus j times the sine of theta. Let's take z to the power of n is equal to e to the power of j theta to the power of n is equal to cosine theta plus j sine of theta to the power of n. This part we can write differently using the identity that x to the power of a to the power of b is x to the power of a times b. So we can write this as e to the power j times n theta. And this is equal to cosine n theta plus j times the sine of n theta. So we have an identity here that cosine theta plus j sine of theta to the power of n is equal to cosine n theta plus j times the sine of n theta. And this is de Moivre's theorem. Now, this theorem can be used to prove all kinds of identities. If we take n is equal to 2 and you write them out, you get 2 identities you should know from high school mathematics, which is a nice exercise in itself. We can also look, and I'll just erase this. If we again look at the polar form, z is equal to r with angle theta. We have with de Moivre's theorem, we know that z to the power of n is equal to r to the power of n with angle n times theta. So for example, z squared is equal to r squared with angle 2 theta. Z to the power of 3 is r to the power of 3 with angle 3 times theta. And we can, for example, take higher powers of complex numbers without having to perform a lot of calculations if we were to write our complex numbers like this. Multiplying this number like in Cartesian form to the power of 5 will be a real hassle, but if we take z is equal to 3 with angle pi over 4, and we want to compute z to the power of 5, this will be a real hassle, but this is easy. This is 3 to the power of 5 with angle 5 pi over 4. So calculating higher powers of complex numbers is made easy with de Moivre's theorem. We can also now also find the expression we previously found for 1 over z. This is z to the power of minus 1, so that is r to the power of minus 1 with angle minus theta, which is equal to 1 over r with angle minus theta. theta. And by using these different forms, it becomes a lot easier to perform certain operations. Now, something to keep in mind. So if we have complex number with angle pi over 4, and I'm going to take the modulus equal to 1, otherwise higher powers will grow too big for my drawing. If I now have z is equal to that, z is 1 with angle pi over 4, then z squared is 1 with angle pi over 2. So if I now start taking powers of this value, you can see that its argument will start to rotate until, of course, I end up in the same position. But I've chosen pi over 4, so I know that in a certain number of steps, 8 steps, I will end up with the same number again. But this is key to what we will be doing now for solving equations and finding roots of complex numbers. So what I've illustrated here is that you get, when you take the power of a complex number, the argument starts rotating. All right, let's remove this. And the good thing about video is you can just skip through this. I could have also edited this out, but this is a single take. We have, as an example, z to the power of 3 plus 4 times z equals 0. Now this is a third order equation, and we would like to find the values for z that for which this equation holds. But we can rewrite this as z times z squared plus 4 equals 0. Then we have as solutions z is equal to 0, or z squared plus 4 is equal to 0. Now, if this one is equal to z squared is minus 4, and we know these solutions to this one, we have z is equal to 2j, or z is equal to minus 2j. So we find that the third order equation with complex numbers will have 3 solutions. Now, any equation of any order n will have n solutions. Some of them might be doubled. If we have x squared equals 0, well, this has solutions, x is 0, and some mathematician will say, yes, but it has 2 zeros. Now, any equation of order n will have n solutions. If there are complex solutions, like what we have here, they will come in pairs which are each other's complex conjugate. Where do we also see that? Well, if we take another example, and we've solved this before, where we have z squared plus 2z plus 2 equals 0, and we use the ABC formula, we get z is equal to minus 2 plus or minus the square root of minus 4 divided by 2. And we found that the solutions were z is equal to minus 1 plus j, and the other solution was minus 1 minus j. You can see these are each other's complex conjugates. So if this is z1 and this is z2, then z2 will be the complex conjugate of z1. But as a final example, what should we do if we have z to the power of 3 equals 8? Now we'll have to rewrite both sides of this equation. We will write z we know that z is equal to r with angle theta because every complex number can be represented as r with angle theta, but we have to look at how to write 8. Well, 8 in the complex plane lies here. So the real axis and the imaginary axis, so it has modulus of 8 and an angle equal to 0. But that angle, we write 0 for it, but we could also write as an angle. So we have theta 0, but we could also add 2 pi. Because the cosine and sine functions are periodic with period pi. We could also add 4 pi or 6 pi. Actually, it is 0 plus 2 times pi times some constant k, where k is 0, 1, 2, etc. So the angle is a unique point in the plane, but not a unique value because of the periodicity of the sine and cosine function. So we write 8 as 8 with angle 2k pi, with k is equal to 0, 1, 2, etc. Now, z to the power of 3, using De Moivre's theorem, is r to the power of 3 with angle 3 theta. And these two things have to be equal to each other. So on the one hand, I know that the moduli have to be equal, and on the other hand, I know that the arguments have to be equal. So I have two equations. R to the power of 3 is 8, and I have that 3 times theta is 2k pi, with k is equal to 0, 1, 2, etc. So all three solutions will have the same modulus, which is 2. And remember that the modulus is a length which cannot be a complex number. So it has to be a real number. So we know it's going to be 2, because 2 to the power of 3 is 8. And we know that theta is going to be 2 pi over 3 times k, where k is 0, 1, 2, 3. And we're starting with a third order equation. So we're looking for 3 solutions. Now, if we take k equal to 0, then we get theta is equal to, well, 0. If we take k is equal to 1, we get theta equal to 2 pi over 3. If we take k equal to 2, we get theta is 4 pi over 3. Now, we already have 3 solutions. If I take k is 3, I will get the same solution as if I get k is 0. So I can stop if I have 3. It doesn't matter if I started with 1, 2 or 3, but it is simply easier to start with 0. So I get 3 solutions. Z1 is 2 with angle 0. I get Z2 is 2 with angle 2 pi over 3. And I get Z3 is equal to 2 with angle 4 pi over 3. Now, if I were to draw these in the Argand diagram, I would find the first one to be here, with an angle of 2 pi over 3, and with a modulus of 2, I would find, so this is Z1, we have Z2, and here will be Z3, and they all lie, the difference in angle is all 2 pi over 3. Now, in a way we were lucky because the initial angle here was 0, so we just add 2 pi times k. If we had z to the power of 3 is equal to 1 plus j, which is equal to the square root of 2 with angle pi over 4. This pi over 4 will become pi over 4 plus 2k times pi, with k is equal to 0, 1, 2, etc. So it doesn't matter that we chose 0 here. If you have an angle which is non-zero, it is in exactly the same way. So that concludes the exponential form, de Moivre's theorem, and solving equations and finding roots of complex numbers or numbers, because basically what we solved here is that the cube root of 8 there are many solutions that if you take that number to the power of 3, you end up with 8. And so we found the higher order roots of complex numbers. And this concludes the theory on complex numbers.